Science further presentations following Excellence Awards. You are welcome to the presentation from the Faculty of Science, Department of Chemistry, University of Buea, Cameroon. The title of the Particle Physics Excellence Award. Welcome to the presentation from the University of Buea, Faculty of Science, Department of Chemistry, titled Green Synthesis by Carambola Fruit Juice Co-Precipitation Route, Effect of Nickel Doping, and Optical Properties of Spherical Copper Oxide Nanoparticles, presented by Dr. Ekane Etape. Science is moving on to responsive matter, that is more particle size, distribution, and morphology sensitive. A popular family of such materials is nanostructured metal oxides, which have gained considerable attention in recent years. They exhibit spherical and special physical and chemical application properties that make them completely different from bulk metal oxides. One of these structured metal oxides is copper oxide, which is a p-type semiconductor with a small direct optical band gap between 1.2 electron volts to 1.8 electron volts. Microstructural parameters such as lattice constant and unit cell volume, as well as mechanical parameters such as crystalline size, specific surface area, microstrain, and dislocation density are governed by their chemical composition and method of particle growth. That is why you can have a particular nanoparticle synthesized by a particular method functional in one particular application, but synthesized by another method misfunctional in that same application property. One way of modifying the chemical composition is by doping the parent microstructure with transition metal elements such as nickel, iron, titanium, lanthanum, and so on. To improve on the electromagnetic properties of copper oxide at room temperature, doping it with nickel-2 has been preferred because of the closeness of the ionic radii of copper, which is 0.72 angstroms, to that of nickel-2+, which is 0.69 angstroms. Many research groups have reported on nickel-doped copper oxides, and although they have used different doping fractions in some cases, and different concentrations, they all observe two principal diffraction planes using XRD diffraction analysis. The planes obtained were -111 and 111 plane, which were prevalent. The multicrystalline nature of the particle obtained is shown by the various peaks that were observed. And basing the estimation of crystalline size on PXRD data and using the Debye-Sherry formula for particle size determination, a review of trends in crystalline size with variation in doping concentration has been contradicted. Basing calculations on the most intense diffraction peak, the one which is -111, or one which is 111, some literatures like Prof et al. 2019 and Waris et al. 2021 have reported increase in crystalline size as copper oxide is doped with nickel-2+. While on the other hand, Amreri et al. 2022 and Kwang et al. 2022 both reported a decrease in crystalline size as copper oxide is doped with nickel oxide. This controversy is very sensitive and interesting. Interest is based on the method of synthesis or particle growth. On the other hand, it can be based on the dopant ionic size effect and the particle size distribution of the inherent particles. Therefore, a new systematic study of the particle size effect of nickel doping on copper oxide was necessary. The application properties of nanostructured metal oxides are varied as much as the method of synthesis. Therefore, we can look at the application properties as a hidden treasure in the field, and the various research groups as the different paths which are heading towards a place that they don't know. This study is adapting a carambola fruit juice co-precipitation method because it is easy to use and makes control of stoichiometry possible. Furthermore, the method is green, environmentally friendly, cheap and affordable, sustainable, with the fruit juice in a natural aqueous state, capable of initiating a wet chemical reaction of 2 or more metal ions at the microscopic level while serving as a precipitating agent. It is also advantageous to us because we are in the tropical Africa where fruits are available, and when not harvested they cause nuisance. The result of this reaction is a polymeric metal organic framework called a single molecular precursor. And interestingly, this single molecular precursor decomposes at relatively very low temperatures, which sometimes run between 300 and 450. Let us look at the experimental procedure, that is the material and method that we used. We used first the carambola fruits. The carambola fruits were harvested from the carambola plant, which is planted and grown in tropical Africa. It also grows in Florida. It was harvested and washed under running tap water, mopped with a kitchen towel, macerated and milled in a kitchen blender, sieved using cheesecloth, and purified further by centrifuge method. 50 ml of the centrifuge fruit juice was placed in a volumetric flask, then transferred into a beaker placed on a heater, which is equipped with a stirrer at 60 degrees. And the precursors were each transferred, that is copper oxide and copper chloride, nickel chloride, were transferred depending on the doping concentrations and stayed for a further 3 hours until precipitation started. The slurry is allowed to age for 3 hours and then filtered over filter paper. The precipitate is then dried at 100 degrees for 1 hour in an oven, and later on calcined at 350 degrees for 3 hours to obtain the powders that we see in the last slide. We decided to analyze both the precipitate and the decomposed samples, and we analyzed the functional groups on the precursors using FTIR analysis as seen in figure 1. And there are 4 principal bands that can be observed, 2 of which belong to the oxalate, and those are the bands between 600 and 960, and the one between 1400 and 1900. There is no band about 300 to 3000 to 3500 because of the absence of water of crystallization, which is characteristic of copper oxide. The one which is at 450 to 500 is a representation of the copper oxide band, while those ones at 600 to 950, as well as 1300 to 1700 are for the oxalate. Upon decomposition, we carried out a thermogravimetric analysis which showed that the sample decomposed at about 350 degrees Celsius, and the decomposed sample was subjected to FTIR analysis, and where we obtained just one principal peak, which was observed between 490 to 500, indicating just the presence of the metal oxide bonds, indicating that the precursor were metal oxalates and the decomposed samples are oxides. Therefore, the precursor decomposed at 350 degrees to the metal oxides. We had to determine the chemical composition of the decomposed samples, and so the sample was subjected to EDS analysis. And as observed here, you can see that all the profiles show the presence of only two metals, that is copper and nickel. And outside that, you can also see carbon and oxygen, which would have come from the precursor, which is the oxalate, indicating that the substance synthesized were pure. To determine the morphology, same analysis were carried out. And from the same micrograph that you see here, we can observe that they were all spherical particles, which were having different crystalline sizes, and the porosity of the material increased with doping, indicating that there was a change in the mechanical properties of the material. To determine the phases of the synthesized samples, it was subjected to PXRD analysis. And as we can see from figure 4, the material was polycrystalline, as can be seen from the multiple peaks, but there were two principal peaks, the peak at 35.832 and that at 38.974, thereabout. Those two are competing, and there were the two conflicting peaks as reported from literature, and that is a great point of our interest. The other bands, which are 32.32, 35.82, 38.98, 49.03, 53.77, 58.50, 61.80, 66.32, are all well indexed with the tenorite phase of copper oxide with space group C2/C1, which match perfectly with JCPD cat number 04005/4872. These two peaks, which we classify them as being dominant, are characteristics of copper and copper nanoparticles in monoclinic tenorite phase. The complete absence of any other impurity peaks, such as those for nickel metal, nickel oxide, or copper 1 oxide, attested to the purity of the prepared nanoparticles, which were very crystalline, as demonstrated by the sharpness of the diffraction peaks. We now decided to determine the particle size of the crystallites using Debye-Scherer equations. Equation 1 as indicated on the slide, and the particles calculated were presented in table 1. If you observe critically using the plane 111, you see that there is an increase in the particle sizes with doping, and as doping concentration increases. When you look at those associated with plane 11-1, or you can call it -111, you see that instead there is a decrease in the crystallized size with doping and with increase in doping concentration, except with the anomaly at concentration 4% of nickel. Also looking at the sample mean particle size, it has an invariable or indeterminable or indiscrete trend, because you see a decrease followed by an increase, then a decrease, and then an increase. That shows that the decrease or the increase depends on whether it is the plane 111 which is dominant or the plane 111 minus which is dominant. When the plane 111 is dominant, there is an increase in crystallized size with doping. And when it is plane -111 which is dominant, there is a decrease in the particle size with increase in doping. That is why the contradiction that we observed from literature is then clear, that the dominant plane determines the trend which is observed, and those two planes are competing depending on the method of synthesis or particle size group. The main observation that we have here to do is that the particle size distribution as a function of the concentration of the dopant is very, very instrumental in the whole show, and that is why we decided to carry out a specific investigation on particle size distribution for various doping fractions. And as observed here, following each doping occasion, there is complete redistribution of the particles. And in a situation where you have a high percentage of big particles followed by smaller particles. The interstices formed by the large particles are inherited by the smaller particles, modifying the microstructure of the material. Either it should be an increase or a decrease, and this causes the stress in the material, which leads to the change in the functionality of the material. And to accomplish this fact, we try to carry out determinations of cell volume lattice parameters for synthesis, for the synthesized nanoparticles as a function of the dopant concentration, using equations 3 and 4 and presented in tables 2A and 2B. And similar trends as observed in the crystallized sizes were observed here. For the -111 plane, we observe that there is a decrease, and for the 1,1 plane, we observe that there is an increase. Therefore, what really matters here is the plane which is dominant, and so we also try to determine the microstructural parameters of the decomposed sample using equations 6, 7, 8, and 9. That is the specific surface area, the density, and the microstrain. And they were reported on tables 2. And looking at, if you look at the second column, it shows you the variability in the dominance of the crystal planes. When it was without doping, the crystal plane which was dominant was the -1,1 plane. And we noticed that by the time the concentrations, the dopant was introduced to 2%, the plane which was dominant was the 1,1 plane. And we observed first an astronomical increase in the microstrain. Also, we observed an increase in the sacs. We also observed an increase in the theta, and all this indicated that with increase in the dopant concentration, there is distribution of particle size, and that particular distribution is characteristic of just that particular percentage of the dopants in the sample. And each dopant concentration has a particular mitigating effect on the material. Looking at the band gap, which is an application, you have the pure copper and the indirect band gaps for the optical transitions of the nanoparticles were determined using the Stokes relationship, and it is shown in the equation presented above. And the observed direct band gaps were 3.01, 2.86, 2.94, 2.84, and 2.97, which have similar trend as those observed for other mechanical properties. The obtained values indicated that there's a possibility of the predominance of the direct photon transition in nickel copper nanostructured material. And in conclusion, in this study, pure and nickel doped copper oxide nanoparticles have been successfully synthesized via precipitation using carambola fruit juice as a precipitating agent, and the results are indicating that unlike most methods of synthesis, the fruit juice method is neutral with respect to the specific particle size growth and particle size distribution. The single molecular precursor is a metal oxalate, complex at relatively low decomposition temperature, precisely 350 degrees Celsius, which favors the control of particle size and stoichiometry. The spherical shape of the particles obtained was retained even under the physical stress imposed by doping and increased dopant concentrations. The PSL results revealed that two predominant diffraction peaks were observed as those reported in literature, and based on the Debye-Scherrer equation approximations of crystallized size, two trends were observed related to the two predominant diffraction planes. Therefore, both reports in literature were correct, but they were as a function of the predominant planes existing, depending on the method of synthesis. The p-excited results SEM and EDX revealed that doping with nickel ions and increasing the dopant concentration introduces physical distortions that modify the particle size and particle size redistribution of crystallites within the diffraction planes. Based on the relative intensity ratios of two predominant planes, both trends reported in literature were observed. The effect of doping is independent of its size, but depends on the particle size distribution effect of the dopant fractions. And finally, the trends in the physical and microstructural parameters which govern material application properties are more a function of particle size distribution in the crystallites than a specific ionic radio effect. Thank you. Okay. Thank you for your keen attention, and we are grateful to Science Father.